Thank you, Samuel. And I will tell this to Laurent, who could not be here today, Laurent Manivel, and Samuel, who really helped me a lot in organizing this summer school and conference. So what I would like to do in this talk is to discuss again these Landau-Ginzburg models that have appeared in many talks and to try and present what Yongwin Ruan, Hiroshi Iritani, and myself are doing in order to treat them in a rather systematic way from the point of view of quantum cohomology and curve counting as in some sense. So actually, as an introduction to Landau-Ginzburg models, I thought one idea could have been to review these examples of mirror symmetry, which in many talks led to consider Landau-Ginzburg models. So let me play this game of having a mirror. And so now we're going to have a défilé of a parade of geometrical objects, and we're going to see what the mirror says. When they pass in front of the mirror, what is their mirror partner? Okay, so, well, as you know, when this is a degree D hypersurface inside PD minus 1, then you have a Calabi-Yau. And its mirror partner has been soon described as an orbifold, soon in the school and soon in the story of mirror symmetry. This group is, in some way, it's an group isomorphic to this ZD power D minus 2. Okay, so this is a case in which a Calabi-Yau corresponds to a Calabi-Yau. Of course, this already led people to consider a orbifold, but this is has nothing to do with the difficulty we are going to encounter when we consider Landau-Ginzburg model. Anyway, let me recall that if you want to give a very simple, if you're not really refined and you want to give a meaning to this, well, then one very simple way is to define cohomology. But then when you define cohomology for an orbifold, you have to be a little bit careful because you have to, well, as people say, you have to orbifold the notion of cohomology. So what is this orbifolding operation? I don't know. It's a very simple thing. So it produces a double-graded cohomology, and let me stress that it consists in going through all elements of the group and repeating the definition of cohomology, but for the fixed part. So adding in all the cohomology of fixed loci. But then you have to take the G invariant. I'm considering G to be an abelian group. G invariant part of this. And you also have to introduce a shift, which we discussed in the course. It's the age of the element G. Anyway, once you have taken care of this orbifolding operation, then this is actually true. And we can move on to some less Calabi-Yau objects. So first of all, I've seen in the talk of Oru and work of Abuzaid, Efimov, Kuznetsov, Katsarkov and Orlov, there were some other objects. X was isomorphic to C star, but that was again a Calabi-Yau situation, and we had a mirror partner that was again C star. But then another object that has been considered is not P1 minus 2 points, but quite P1 minus 3 points. And then we are led to look at what people call pair of pans. Okay, and then we are out of the Calabi-Yau setup. And in this case, X being this geometrical object, we discovered, or they discovered, that what we should look at is a new type of object, which consists of a space equipped with a function, usually called potential, or in the talks of Junli, a cosection. Similarly, in Mulase course, there were some double Hurwitz numbers leading to some very interesting enumerative geometry, and they also led to had a mirror partner, and the mirror was something looking like a function on a space, a one-dimensional space, and the function was again a potential, which I usually denote by W, and was having that space. And this was described as the results of a conversation or between Boris Dubrovin and, anyway, it appears in this nice story that Mulase tells us in his course. Okay, so now what one would like to do is to try and see what happens if instead of presenting a geometric object in front of the mirror, I put a Landau-Ginzburg model inside of the mirror. And then I want to know what is the mirror of that Landau-Ginzburg model. I mean, what I'm trying to convey is the idea that what we are doing with Young in following ideas of Witten is that here we are starting considering very simple Landau-Ginzburg models, such as, for example, the case in which I have an affine space, or just C. And here W is going to be x power d. So what is the mirror of that Landau-Ginzburg model? So what we find out is that if X is this data, the mirror should be, well, what people find out. I mean, this is rather widely treated in the literature. Since W is invariant under the action of the cyclic group, then you can consider this orbifold. Okay, and then you can wonder if this is actually the mirror of that. Well, one test, as I said, not very refined test, is to try and see if at the level of those invariants we actually have this behavior. It gives me, of course, an excuse to introduce one of the main invariants of Landau-Ginzburg model, which has been already studied, and it's matrix factorization. So what are matrix factorizations? They are vector bundle, if you want, or locally free project sheaves on Y. So let's think about them as vector bundles, E0 and E1 on Y. But they have the extra data of delta 0 and delta 1. Now you're going to think that the composition of these two arrows gives a two-periodic complex. And in fact, this is not the case. When you compose delta 0 with delta 1, you get W times the identity of E1. And you compose delta 1 after delta 0, W times the identity of E0. So this is what a matrix factorization is. And now you have a category of those things. And when you pass to cohomology, well, more precisely to Hochschild cohomology of this, then you get the cohomological invariants I would like to study. Well, if you want, you can take this as a definition. I'm going to tell you what happens precisely for Oxford cohomology in this case of an isolated singularities. As you see, we're not very ambitious. We are restricting ourselves to Landau-Ginzburg model, which have a single singularity, isolated at the origin. Not quite like this case in which I didn't say W was the product of the three variables. So the critical locus is given by the axis. And here, what do I have? Here I have a Milnor ring that computes for me this invariant. Well, actually, people usually don't quite consider a Milnor ring, but present the Milnor ring at least in this form. And these are forms, if you want. You can say that these are forms. Anyway, this is just a matter of how we present things. This is the Milnor ring. Or another way you may be more comfortable with is that this is just the relative cohomology of the Milnor fiber, which is the fiber of this map when you consider it off the origin, which is this critical, where the critical locus occurs. Yeah, sorry, let me zoom this for people over there. Yeah, you have to take t different from 0. And now you have a relative cohomology, which again, well, actually it's concentrated in degree 1. Because we are taking relative cohomology. And okay, so let's, I close this window here. And I make it explicit what I mean by this writing. I mean that I have x, c, dot, dot, dots, up to x power d minus 1 c. This is the dimension of the, as a vector space of the cohomology. And since each of these generators, these d minus 1 generators, obtained by just modding out this is minus 2, d minus 2. Okay? So each of these generators should actually yield something of total degree 1. Well, the actual degree is 1 over r minus 1, 1 over d, d minus 1 over d, up to d minus 1 over d, 1 over d. Okay, so that's the cohomological invariant. So now that you have the idea of what you normally do for a Landau-Ginzburg model, let's compute the same thing here.
Is it generally cohomology
No, it's related, but I have to, for example, let me show you this case. You have to do something to this Milnor ring. So yes, no, I would say that I have examples where this is, you have to modify slightly. But anyway, that's a good idea to bear in mind. I would say that this is probably where you have to find your invariance. And then, but anyway, yes, it's a question that I ask myself every day. So let's see if I manage to define for this, to find out for this geometry what is, like this setup, what do I get? Well, again, there is an orbifold that comes into play, so you have to go back to this operation, which means that you have to add in the same to the computation where you are considering all elements of ZD, contribution of the Milnor ring for all fixed data. And then, of course, you have to take the ZD invariance. And once you do this for the trivial group, you realize that you recover this, but none of those elements is fixed by the action of ZD. So nothing remains. And so the only thing you actually are left with are one-dimensional spaces which are attached to non-trivial elements of ZD. So I could actually take off straight away the trivial elements here. And what I'm left with is one generator attached to 1 up to one generator attached to d minus 1. Okay, so now if you compute and if you add in this age shift, then you get classes of degree pp of type 1 over r, 1 over r, d minus 1 over d, sorry, I keep on writing. D minus 1 over d. And you actually have a match with what? With the b degrees over here. So it really happens what I just announced, that the Hodge numbers here switch in the way I said. The dimension of that Landau-Ginzburg model should be 1, and therefore we have this formula. H pq of x is becoming h1 minus pq of x2. Okay, so this was just a game that we have played with a little, very simple Landau-Ginzburg model, which I would like to treat as an atom of this mirror symmetry. And now the natural thing to do is to say whether I can derive from that corner of the blackboard a statement involving mirror symmetry to a wider extent for varieties, for hypersurfaces, for complete intersection. And indeed, I can. So there is actually work of physicists Berlund and Hubsch Berglund and Hubsch, who actually, and I should add Mark Kravitz, who had to take care of a few parts of this work which were not defined. He was a PhD student of, he was doing this when he was a PhD student of Yongbin last year. And now we're going to consider we're going to present, again with my mirror here, a mirror construction coupling W with another W and G with another G. And as I said, Berlund, Hubsch, and Kravitz do not bound themselves to those kind of models, but they put them together. So what we are going to do here is that typically we're going to have a sum of things like this. Now, one thing one can notice is that Milnor ring behaves very well when you have some of things that are involving disjoint sets of variables. This is actually typical in singularity theory, and relations like this are often called Thom-Sebastiani sums, Thom-Sebastiani formulae. So this is what we're going to try and do to infer from that example what this should be in general. Another thing one should consider is that a very small group, i.e. a trivial group, became here a very large group, i.e. the whole group of symmetry of our. This kind of feature is going to appear again here. Okay, so now some notations. Yeah, tell me. What is it?
You can't tell the I's from the J's.
Oh, yeah, that's very good. Actually, let me point out one other thing that is rather unpleasant. So those people are unable to treat cases in which the polynomial can be expressed in more monomials than variables, which is a very strange condition. So I must admit this condition is strange, and we stay there. Okay, we're not going to say more about other conditions. Of course, one can speculate. But then what it means that the singularity is isolated? Well, it means actually, and well, that the polynomial is non-degenerate. It's actually something that you can say in terms of the matrix here. And I don't know if it's exactly equivalent, actually. But anyway, so let's say that I would like to have this data. The matrix keeping track of all the exponents. And I assume that this matrix is invertible. And now the notation is that if you look at a column mj1 up to mjn, then you can produce a matrix out of this. Sorry? Yes, it's invertible. No, no. I mean it's invertible in rational numbers. Yes. So those are rational numbers. Therefore, as Etienne rightly pointed out, this is not a trivial matrix. Okay? So these are not integers, and here you have rational entries here. You have a diagonal matrix, which I'm going to call rho j, and it turns out that if you apply this matrix rho j to your variables, well, then W remains invariant. More precise, okay, so that's already something one has to consider. And more precisely, if you want to consider all the automorphism doing so, well, that's spanned by rho 1, rho n. Okay? So that's a very simple way to detect those elements. And of course, if you take the product of all those, let me see. Well, I'll let you do it on your own. One other thing I would like to introduce as a notation is that anytime you have a matrix, you can think of setting up a pairing. The pairing is very simple. Well, if you want to write column vectors, then you have to do this. But I'm going to look at this pairing inside Q mod Z. And now I'm ready to tell you in 2 words what is W and what is G. Well, W is just the sum over I of the products over I of xj mji. What happened with respect to that W is that I have transposed the matrix. Nothing but than that. Nothing but that. I just have transposed the matrix. And what is G? Well, it's orthogonal to the other G with respect to that product, or pairing. So since groups are, G a priori was a subgroup of this guy, it can be expressed in terms of these elements. So its element can be regarded as vectors. And now you can consider all the vectors that are paired with that and are orthogonal. Yes. Sorry? Oh, cool. Thank you. Anyway, so we sort of understand each other. You want to see?
Not exactly the same expression as you gave for W.
Right, but when I come here, instead of writing ij, I write ji.
Okay.
So it really does really funny things with which you can amuse yourself if you have to take lots of airplane to go home. I mean, try and take this. Oh, let me see. So, yeah. So this is a matrix, but it's also polynomial. Okay? But now you transpose this matrix. Yes, thank you. Now you transpose this matrix. And now this is again a polynomial, which ends up with a very funny 4 here. So if you look at this polynomial carefully enough, it's hard to make sense of this polynomial as a homogeneous polynomial. Okay? But it is a homogeneous polynomial, only you have to consider a space with some suitably chosen weights that I'm going to make up. But actually, I think they're actually correct. And it has degree 256, something like that. Anyway, so this example is a kind of good example to give to people. And it tells you how to transform not only, well, to transform this Landau-Ginzburg into its dual. This was just a sketched example. I'm not going to develop it in detail because as you see, I would like to get back to geometry. Now I'm fed up with Landau-Ginzburg models, and I would like to see if this detour in the realm of a Landau-Ginzburg model is useful for something. And the idea would be that at the end of this trip, I'm going to get back to Calabi-Yau geometry. So that's what the Landau-Ginzburg-Calabi-Yau correspondence is there for. It relates the Landau-Ginzburg model to a Calabi-Yau space. And how? Well, in the simplest possible way. The one thing you should... can I erase this example? No, some people are saying no. Can I? Yeah, okay. I leave you the matrix if you want to. So remark. So you give yourself W as this with this data, then there exists a certain degree and a certain sets of weights such that W lambda W1 x1 W and xn is equal to lambda D W. In other words, this is a weighted homogeneous polynomial. And now let's assume that the sum of the weights is equal to D. Then I can look at this hypersurface inside a weighted projective space, and this is a Calabi-Yau space. And I can also look at this potential here, mod A group, which is spanned by the matrix CDW1, CDWN, mapping to C via W, okay? And what I claim here is that those two things are entirely equivalent. Meaning, if you want to stick to our cohomological point of view, that if you compute the Hodge diamond, you're going to find the same Hodge diamond. I deliberately wrote them horizontally. There's nothing to do with mirror symmetry. It has to do with the fact that the same geometrical object can appear under several different setups. And those setups should be equivalent. They should be equivalent in the cohomological sense, but they should be equivalent also in the categorical sense, because there is an equivalence between derived category of the hypersurface of oops, got it wrong. Derived category of coherent sheaves on this hypersurface and the matrix factorization since we are in a projective setting, I should add in this grading and the group of these two things. So there is an equivalence between these two sides, which is also an equivalence at the level of categories. And well, natural question is whether I can have a mapping going from the K-theory of that categories to the Hochschild cohomology, as I discussed. And since I'm going to use this in the next part of the talk, let me tell you what this mapping does when I consider a very simple matrix factorization. This is going to be an appetizer for the rest of the talk. Sorry? Yes, okay, that's a very kind question. What happens if I take G here? Well, then here I'm considering a group which is just my G mod out by ZD. So, thank you. So this is a theorem of Orlov. Oh, maybe that now that I put the G, I'm a little bit less able to say. But without the G, I'm sure. Yeah, well, I actually don't know on the spot. But I would.
So that movement is not unique.
Sorry?
It's not canonical.
Yeah, so that's true. There is also, this is another observation that is going to be useful for me later, that the functors that you can set up between these two categories are not, there is a certain integer parameter that you need to set up these functors. There is an auto-equivalence identifying them, auto-equivalence of one or the other category, but still, there is this abundance of the functors. And this is going to appear in the rest of the talk. Okay, so
What is the theorem of Orlov?
this one. Yes. Yes. The equivalence of triangulated category from this and this. Without taking K0, sorry, I understand your questions. No K0. I was just trying to say what happens if you now have a matrix factorization and want to apply the Chern character. And this is going to be useful for me. So this is my personal moment here. I'm just doing something, but maybe it's interesting to see an example. So E0 and E1 are both trivial line bundles on Y. And now I'm getting back to that kind of setup. But delta 0 is going to take a section and multiply it by x. And delta 1 is going to do this. So when you get the composition of this, you do get, oh, sorry, here I keep on writing R. I wanted to write D. When you get the composition of this, is actually equal to this. Keep on writing R. Okay, so now we are ready to, and what happens? Okay, so I want to have a ZD action here that acts trivially on this and in a compatible way on this. And what is the Chern character of all this data? Well, that has been worked out by many people, Diekerhoff, Walker, and recently there was a paper of Poliszczuk and Weintraub, which actually compute this in order to give an algebraic definition of the theory, of the curve counting theory that I'm going to introduce in a minute. And their computation says the following, that the Chern character is going to be of this, in this specific case, Now, as you notice, when I hits 1, I don't get anything, which is good because my space there has no space for Chern character supported on that. Sorry, what is D? D is W. D is oh. When I is 0, I don't get anything. That's what I want to say. Oh yes, 1. I sort of probably must have said. I want to say 0. Thank you. So now let's wipe everything off and let's pass to a higher level, which is the level in which curve counting is taken care of. So at a less elementary level, we would like to consider an equivalence between Gromov-Witten theory of the hypersurface XW and a theory defined by Fan, Jarvis, Rouen, following inspirations of Witten, of this. And let me just recall that Gromov-Witten theory has been computed in these cases. Let me restrict for simplicity, to this, a Fermat polynomial defined as like so. And here I go quickly through this theory of curves, which possibly are nodal and map into PW by a universal map. And of course, they have markings, and the composition with these markings gives rise to evaluation maps. And now this is an untwisted theory which says nothing about the hypersurface, but if you install a line bundle and you consider this theory with respect to our function W that is a generic degree D polynomial, then you can define Gromov-Witten invariants, which are usually written like this. And they are nothing but integrals over the moduli space of genus 0 maps to this target of degree D, which should be in the notation 0, n, and d, of the following cohomology class. Okay, so here I'm pulling back hyperplane classes which I intersect with themselves, I h times, and that these are the standard psi classes, and I want to cap this with the Euler class or top-Chern class of the direct image of the pullback of O d. Now it turns out that for degree reason, this thing is actually a vector bundle. So that's Gromov-Witten invariants, and we can compute them. As I said, we could easily compute them if there were not this nasty term, but this has been taken care by Zhang in the orbifold setup and Coates-Gieventhal in the non-orbifold cases, in a certain formalism that tells us that, yes, I want to quote also Corti, Coates, Corti, Coates, Lee, and Zhang, and also Iritani somewhere, and then we are done. And I would like to stress that all these people, maybe So Coates could not come, and but we're going to invite him some other time. He had very good reason not to come. Okay, so let me now go through the Fan-Jarvis-Rowan-Witten theory. Okay, so again we have a moduli space, and the moduli space is a space of curves with line bundles. But then this line bundle should respect this W structure, which, for simplifying things, I have decided to be a weighted homogeneous polynomial of a very simple kind. In this specific case, which is not the most general of the theory, what we are actually doing is requiring that those line bundles are roots of the canonical bundle. Or more precisely, log canonical bundle, but this is something you can ignore if you haven't seen this. It's really just log bundle twisted at the marking. So now what is the local picture of this? Well, I take a point, and I have all those lines here from 1 to n. N is the number of variables. And I want to look at how this point, which is an orbifold point, because every time we have those kind of curves in Gromov-Witten theory, we are led to naturally to consider orbifold points. Then I want to consider the character acting on this line. And actually, by the way, if you set up a matrix with this character, it gives you an element of the automorphism group of W's, which is something you may want to think about. Precisely the automorphism group that appeared in the previous part of the talk. And now what is the invariant of this theory, which carries out some curve counting? Well, it's a W0n. Just one thing. So okay, we have a nice moduli space. Let's start looking at it 1 second. Let's get rid of Gromov-Witten theory for a second. Okay, so we have a nice moduli space. Why don't we think about it 1 second? There are stabilizers that act in this way. Now you may ask the natural question whether inside the WGN there are substacks which I would like to call like so, that are identified for any G inside out W containing ZD. And what is their feature? Well, every time the local picture at each marking is one matrix like so, which actually belongs to G and not to automorphism as a whole. You may want to restrict like that. And in fact, it is true. And if you want one special case of this construction is the case in which you consider ZD spanned by this matrix. And that case is actually the case of curves paired with a line bundle whose D power is isomorphic to the log canonical bundle. Just one line bundle. This line bundle is the same as giving several line bundles, because you can nicely identify in an obvious way L to the power of W1, L to the power of Wn. Okay? So then you actually are considering a substack of, or a subspace of that moduli space. And since this was the group I would like to consider from the start, here are the invariants. I integrate on this WGN 0n Z D, the class is psi1 to the power of I1, and I restrict this to this. So what happens is that this local structure here, chi1, chi, oh, you cannot see. Well, let's see it here. So if you take this stack here, it has some local action at each point, chi1, chi n, which are the way the stabilizer acts on the lines. Okay? And now I'm requiring that this stabilizer act precisely as I1, In, data which are incorporated in my Gromov-Witten notation. Okay, so that gives numbers, which would be very easy to compute, but there is, again, a class that we have to take care of, and that's the virtual class, which is the higher direct image of L power Wj. Summed for j going from 1 to the number of variables. And again, as in the case of Gromov-Witten theory, one would like to compute those numbers by defining an operator adding this data to the theory. And let me just sketch the idea. Well, there is a generating function of the untwisted theory and we have defined an operator which is very simple and has been defined by Dmitry Zvonkin and myself. And it actually yields, after a few steps and a nice generating function, which we call the I function of FGRW theory. And what is that supposed to mean? Well, it means that this can be actually looked as some can be obtained, can be used to obtain partial derivatives of the generating function, which is the Gromov-Witten, the van Jarvis-Gromov-Witten potential of this problem. And what we find is that it satisfies the Picker-Fuchs equation. Which is the following. where D is some operator like this. And it's the same Picker-Fuchs equation that appears already in Gromov-Witten side.
I equals J.
Sorry?
I equals J.
I equals J. K? No, I equals J? Yes. Oh, I see. Okay, so what this means is that we have two functions that are actually satisfying the same Picker-Fuchs equation, and we are going to now present this in a theorem which has been discussed by Yongbin under the name of global mirror symmetry theorem. So let me. So the situation is the following. We have again a mirror. And let's focus on the case of the quintic. Even the Fermat quintic, if you allow me. And let's consider the case of the dual, which I already told you about. And now the dual can be actually deformed along a P1 line, starting at 0 and ending at psi equal infinity, where psi intervenes as follows. So those are all fixed by my action of Z5 power 3 and gives us a family of mirror Calabi-Yau orbifolds. And now I can consider here around infinity a lattice which is the odd cohomology of this variety inside the complex cohomology, odd cohomology, of this variety. So you see, you can consider the odd cohomology, and you have a lattice. Let me. Have a lattice inside this four-dimensional vector space. And it has some non-trivial monodromy vectors. It is the Gauss-Manin connection, which makes it a vector bundle connection and non-trivial monodromy. So what you do here, what Giventhal and Liang Yu Yao did here, was to identify even cohomology with Dubrovin connection, which is four-dimensional for the space we started from, with this space. And now we're going to do the same here. What Yongbin and myself have done is to identify this space, this even cohomology of this potential with respect to the group ZD with some Dubrovin connection, and this identification is precisely given by the fact that the I function satisfies the same figure. You can say that. You can see I function as the projection of the period vector on a 4 flat sections provide basis for this vector bundle with cluster. And now that we have an identification between this flat section over there with flat sections over here, and we have the same identification here, one can actually consider whether the parallel transport of this flat section giving a basis on this side can be compared with that other side. In other words, whether there is a matrix U that transforms the I function, analytically continuous I function of the theory of Fan, Jarvis, and Rouen to the I function of Gromowicz. And this was a theorem which Youngmin and myself have proven and provides this matrix, but does not give any explanation for the fact that this matrix is actually symplectic. And the reason why it's symplectic is something you can find. Equivalence between derived categories of coherent sheaves from this and matrix factorization of W ZD, and this descends via the Chern character and the gamma class that has been introduced by Iritani to a cohomology isomorphism between these two spaces. Okay. So a cohomology isomorphism. And as someone pointed out, the definition of this depends on a certain infinite parameter A. And now, what I would like to say here is that the map U that we have found here that relates the fiber of this vector bundle to the fiber of this vector bundle without going, which we have found by going through this B-model picture, is the same as the map that we get up there relating to this topological. This is the theory that Hiroshi, Iritani, and Youngbin, Rouen, and myself which says that U equals to P A. But now the natural question is which A? Well, you can arrange things so that you have an A that matches it, but that's not actually what we do. We actually find out that if you carry out analytic continuation along a different path between 0 and infinity, since there's a local system here has singular points, you can always choose a different path, and there is actually a range of paths depending on the integer parameter z. So you can also have this parameter here. Then the theorem that we're proving says that this equals that. And it provides an explanation for the fact that UA is a symplectic transformation because it comes from a categorical framework where on both sides we have the Serre functor that guarantees that which is respected by Orlov, and it guarantees that we have a symplectic form which is preserved. So this operator is symplectic, it can be quantized, and therefore it yields a higher genus correspondence between two things that are still widely unknown apart from cases in genus 0 and 1, and by mathematicians, by physicists, for physicists, apart from cases which are for genus higher than 51. That's all we know. Thank you.
Evidence that U is symplectic, or that's a theorem?
Here.
Oh, okay.
It is, yeah. So
The name I heard, so Irvitani, U is an Irvitani, and
Youngmin
yeah.
are proving this.
Sorry? U is an Irvitani and Youngmin.
Yes, that's right.
So you take for your higher genus prediction A.
Right. Oh, I see. Yes, I suppose so. Yes. So you want to have to think whether it simplifies things to look at one A rather than another.
So whenever you take that visa,
Yeah, you need a choice of A.
I just wanted to, like, I asked you a question about this.
Yeah. No,
Well, no, you surely think that there is like safety there. From technology, it's not necessarily lazy. Probably something like this, the
right. Oh, I see.
And then you get like this Miller ring is one say if it's defined like C star or something, then so what I want to say is like it seems like we get Miller ring
Oh, I see,
only
sorry.
as a sum, it's not like
Only as a sum.
yeah.
Yes. Okay.
But you had like an equality. What's an equality in that particular case? Or
Do you think that this is much bigger than? Yeah. Well. Yeah. I suppose so.
yeah, it's bigger than the Miller ring.
Right.
Theory.
For sure.
Amazing talk. And this, no, it really was. I mean, really, as a culminating talk, it was really wonderful. Like, also people around me, we found it really a wonderful experience. And
Thank you very
the
much.
whole,
Thank you very much.
Well, this whole experience is wonderful. And this conference, really, it packed together so much of the research development. I'm so privileged to have been able to